thanks for checking in. This lesson, which happens to be the last lesson in our unit, is called Similar Triangles and Missing Measures. Let's just get right into it. A couple definitions here on this first screen. First definition is for similar figures. What are similar figures? And specifically today, we're going to really be looking at similar triangles. Similar figures are figures that have the same shape, but they are not the same size, but they are proportional. So it's important to realize that similar figures are not the same size, but they are proportional. Here's how I like to think of similar figures, and specifically today, similar triangles. It's like a big triangle has a mini-me, right? So it's like a big figure and then a proportionally reduced or a proportionally smaller miniature version of itself, where all the measurements for the lengths of the sides of the shape have been shrunken down or reduced down by the same amount. So maybe if you compare the little triangle here that you see, triangle ABC, to the big triangle that you see, triangle DEF, first of all, are they the same shape? Well, yes, they are. Now, obviously they're not the same size. But when we compare them, what we notice is that they are proportional. The smaller guy is, in fact, a reduced version of the big guy. And if I'm looking at the measurements of the sides, which is really important when you're looking at similar figures, I notice that the sides of this triangle, the little guy here, ABC, are all 3. And then I look over at the big guy, triangle DEF, his measurements are all 6s. So if I look at that and I compare going from a measurement of 3 to a measurement of 6, that's twice as big. And over here that's a 3 and this is a 6, that's twice as big. And down here that's a 3 and this one's a 6 and that's twice as big. So this is proportional. The big triangle is twice as big as the small triangle. So it's proportional. It is in fact like a mini-me. Next definition is for an idea called corresponding parts. Corresponding parts are angles and sides on different figures, but they're in the same position. Okay, so if you remember in the previous lesson we talked about corresponding angles. Here, I'll draw a quick little sketch for you. We talked in a previous lesson about corresponding angles, where we had like angles 1, 2, 3, and 4, and then we had angles 5, 6, 7, and 8, right? And we were talking about who corresponds with who. These angles, who's in the same position, but in a different location. It's kind of a hard thing to put into words. So I bet you remember, if I circle angle 1 and I ask you, who corresponds with angle 1 down below in the other cluster of angles, between 5, 6, 7, and 8? Who corresponds with 1? Who is in the same position as 1? Just in a different location, and that would be angle 5. So corresponding means you are in the same position within your group or within your shape. You're just not on the same shape as who you correspond with, or you're not in the same cluster of angles as the angle you correspond with, okay? So, looking at triangles here, I'm looking for angles that correspond with each other, and I'm looking for sides that correspond with each other. Ready? We're going to kind of color code this. Looking at the small triangle, I'm looking at side AB. Who corresponds or matches up with or is in the same position as AB on the big triangle? Well, that would be DE. Those guys are corresponding. They are in the same position within their shape. How about BC? Who corresponds with BC on the big shape? That would be side EF. And who corresponds with AC on the big shape? That would be DF, right? So those are corresponding sides. We can do the same thing with angles. Look at angle A. Who corresponds with angle A? Angle D. How about B? Who matches up with B? That would be angle E. And then finally, C corresponds with F. Now, this really does become an important concept in a little bit when I start showing you how to make some calculations to find some missing measurements. You have to be able to find the corresponding parts between these triangles. Of course, it's not always quite this simple. What they're going to end up doing is they're going to take some of these shapes, some of these triangles, and they're going to rotate them a little bit, and they're going to flip them and turn them. So it's not always quite this easy to match up who matches up with who or who corresponds with who. Sometimes you have to really examine the way that the triangles are drawn and figure out if I were to turn this triangle a little bit or if I were to flip it the other way, then it would be a little more easy to see who corresponds with who. But it is important to know what corresponding means. Last definition right here. Congruent. Congruent means having the exact same measurement, meaning that they are equal. And this is important to talk about because what you're going to see a lot of times when we're talking about similar figures or similar triangles in this case is that when shapes are congruent, sometimes they use these weird tally marks. They call them tick marks or tally marks. And they use these weird little like arcs on these angles to indicate equal measurement. So if I'm looking at the sides of angle ABC, triangle ABC, do you see how each of the sides has one tally mark or one tick mark? Right here, right here, and right here. Because they each have one, that means whatever AB is, whatever it is, we don't know, but whatever its length is, BC is the same and AC is the same because they each have one tick mark. Okay? And if I look over at triangle DEF, that side length is 2 tick marks. However much that's supposed to represent, it's 2 tick marks. And EF is also 2 tick marks, and DF is 2 tally marks or 2 tick marks. So all those sides are the same measurement, whatever their measurement is. And it's not the same measurement as triangle ABC, right? ABC has 1 tally mark, DEF has 2. Now let's look at the angles. The angles, let's look at angle A. He's got one little arc here. That means that's his measurement. Whatever it is, it's being identified as one little arc. Look at the big triangle. Does anybody over there have one little arc? D does. So A and D are actually congruent to each other. Whatever A is, D is. Look at angle B. Angle B has 2 little arcs. Not the same as angle A. Different measurement. How about on the big guy? Anybody over there have 2? Yes, angle E does. That's because they are congruent. They have the same measure. So B and E would have the same degrees. Jump down here and look at angle C. He's got 3 arcs. Not like anybody else in his shape, right? His degrees don't match angle B, and his degrees don't match angle A. Whatever his degrees are, they're different than A and B. But if I compare him to the bigger triangle, triangle DEF, you look at angle F, it has 3 arcs, so angle C and angle F are congruent. Now, because the angles match up, the congruent angles A and D are the same measurement, and B and E are the same measurement, and C and F are the same measurement, and the sides would happen to be proportional, we say that these triangles are similar to one another. The small one is in fact a miniature version of the larger one. And down below here on this screen, you can see that I've written what's called a similarity statement, or well, let's call it a similarity statement. And what it says is triangle ABC is similar to triangle DEF. Now, no worries about that, really. I'm not going to make you write any similarity statements, but there is such a thing, and it does exist. So if you ever hear about a similarity statement, they're just telling you that the 2 shapes that you're looking at, the 2 figures that you're looking at, are in fact proportional. They are similar to one another. Okay, so you should definitely write this down. This is really, really important stuff. When figures are similar, you need to remember this. their corresponding angles are congruent. So the angles that match up from one shape to another, those angles have to be equal to each other. So if angle A on the small triangle matches angle D on the big triangle, if they're corresponding, they need to have the exact same degrees, the exact same measurement. They are congruent. However, corresponding sides are proportional. Not the same measurement, right? Side AB corresponds to side DE, but they're different lengths. They're not congruent to each other. But AB is in fact a smaller version of DE, and it is smaller by a certain ratio. You'll see what I mean here a little bit more in a minute when I start doing the actual math behind this. And this is the actual math. It says given two similar figures, you can use a proportion. You remember what a proportion is? It's two equal fractions. Two equal ratios or two equal fractions. You can use a proportion to find the measurement of a missing side of one of your similar figures. Now, I'm going to teach you how to set up this proportion. I just reminded you that a proportion is two equal fractions or two equal ratios. When you go to set this up, you're going to take a measurement from the small triangle and find who it corresponds to on the big triangle, and the big triangle's measurement goes on bottom. So you're going to hear me say small over big. Again, it's all about corresponding sides. So the side on the small triangle corresponds with what side on the big triangle, and then you set it up. Small measurement over big measurement. So you'll have real numbers here. You're going to set that equal to, again, something from the small. Who does he correspond to on the big? That number goes down below. So small over big equals small over big. And then it tells you that one number will be missing, and we're going to use cross products to solve for that missing value. Do you remember what cross products are? It's when you multiply diagonally this way, and you get these two answers, and this answer should be equal to each other. If they're not, then you do not have similar figures. Okay? Let's just see what in the world these problems are going to look like. It says, state if the triangles are similar. Set up a proportion. Okay, so I'm looking at these triangles. Oh boy. See what I mean? They're not drawn the same way. One of them's been turned and rotated a little bit. So first of all, we have to do some investigating here. Now let's remember the two things about similar figures. The corresponding angles are congruent. Do you see any angle measures here? Because I don't. So that goes out the window. We cannot look at angle measures because they're not given to us. So we're forced to look at the sides. And in corresponding figures, or similar figures, corresponding sides are proportional. I'm getting all my words twisted. So I'm going to look at these two triangles and I'm going to figure out what side goes with what side. Can you see what they've done with triangle RST? See this guy here? I'm going to highlight him. How would you get that to look like triangle PQR? You kind of need to flip it, wouldn't you? Right? So can you imagine taking this triangle and kind of flipping it down so that it matched up? All right? So now hopefully you can see what side goes with what side. Corresponding sides. And what we end up seeing, hopefully you see, is that side RT corresponds with side PR. Those two sides go together. So this guy corresponds with this guy. And side RS corresponds with side QR. So 12 corresponds with 36. Okay, now we're going to set up a proportion, and it's going to be small over big, small over big. So take a measurement from the small, 12, and who does he correspond to? We decided it was 38. That's small over big. Set it equal to small, again, this side is 12 again, over big, which is 36. Small over big, small over big. Now we're going to use cross products. Get your calculator ready. When we multiply that way, we get 432. If you multiply this way, you should get 456. Now, do you remember what I told you about cross products? They should be equal. Is 432 equal to 546 or 456? No. Guess what? These are not similar because their sides are not proportional. So your answer is not similar. The sides are not proportional. Let's look at this one. Again, I don't see any angle measures. There are no degrees provided. Oh boy. So we have to do corresponding sides again. Ready? Let's circle some colors. Let's look at the bottom here. Let's look at the small triangle. See the 3? Do you see who he would correspond to on the bigger triangle? Can you imagine flipping that thing over? Yep. 3 goes with 6. Small over big. How about 4? Who does 4 go with? 4 goes with 8. Let's see. Small over big. Let's do cross products. 6 times 4 is 24. 3 times 8 is 24. Are they equal? Yes. So these are proportional. Oops, don't say proportional. They are similar. Yay, we found some that are similar. Last one. Well, last one on this page. Whoa! I don't even see any measurements, do you? I don't see any side lengths, and I don't see any degrees. But I see those little arcs I was talking about. First of all, we got to figure out, we got to flip some triangles over here to see who corresponds with who. Who do you think corresponds with angle D? What do you think? I guess it kind of depends on how you turn the shape. You could say angle A if you rotated it, or you could say angle C if you flipped it. Well, either way, D should match up. Angle D has 3 arcs. And if you say he matches up with angle A, does angle A have 3 arcs? No. Does angle C have 3 arcs? No. And remember that in similar figures, the corresponding angles are the exact same degrees. So the way I see it, angle D does not match up with A or C. They're not congruent angles. So they are not similar. Because the angles are not congruent. The corresponding angles. The angles should match up perfectly with their degrees or with their arcs, and they do not. Last one. Last page. Find the missing value in the similar figure. Okay, remember small over big, 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 small over big. Think that sunk in? I hope so. Trying to figure out the measure of x. Okay. Well, small over big, small over big. Look at the small guy. I circled the x. Who does he correspond with on the big guy? Well, x goes with 10. Small over big. How about the 4? Small over big. Who does he correspond to? The 8. Small over big. Cross products. Let's see what happens. 10 times 4 is 40. 8 times x is 8x. These are equal to each other. So now you say 8x is equal to 40. Hey, we have a nice little equation to solve. Divide by 8. So those 8's cancel. Got your calculator out? Or maybe you know, hopefully, your times tables, and x has a value of 5. So 5 is that measurement, which makes sense, because if you take 5 and compare it to the 10 over here, that is 5 times 2 is 10, and if you look at the 4 and you look at the 8, 4 times 2 is 8. So the big triangle is twice as big. It is proportionally bigger than the small triangle. Okay, there's just one more. Look at this guy. It's a triangle inside a triangle. That's all right. It's still a small triangle here inside a big triangle. We can still do small over big, small over big. Ready? Let me put some colors here. I see small corresponding with big. Small over big. I see small, the one that I want to find, over big, the one that it corresponds to. Small over big. Cross products. 20m. 15 times 24 is 360. They are equal to each other. How do you solve for m? Break off that 20, right? Divide by 20. Missing measurement down here is 18. We used a proportion and cross products to find the missing measurement on similar triangles. And the way we set up that proportion is small over big, small over big. Cross products. Set them equal, solve for your variable. Here's what it says. We're, of course, going to have a worksheet for this lesson. We're going to work on it for 2 days during class. Remember this. And cross, multiply, you'll get some answers, and they should be equal to each other. Okay? Awesome. I'll see you in class.